Hey TJ Machine Learning Club. So last week we went in depth on how convolution works. So today we're going to continue on our convolutional neural network series and kind of ended off today discussing the network and kind of applying our knowledge of convolutions to see how convolutional layers are actually implemented in a full CNN. So just to kind of start off, remember like the reason we chose convolutional layers over fully connected, denser, fully connected layers initially was to take advantage of the spatial structuring in an image. Like essentially just the idea that all the pixels close together are going to be more correlated than pixels farther apart. Because in an image, for example, the placement or of like where things are in an image is important, and if you have some sort of figure in an image, all of the little pixels near that spot in the image are very valuable, and it should be considered that they are close to each other, and we need to take into this spatial structuring in account. So by sliding a kernel across an image, we're considering only the small regions of an image at a time, and this kind of helps looking through each part of the image and figuring out, trying to understand some sort of patterns. And by using the convolutions, we even address the problems of translations, because in a standard fully connected layer, the network might learn how to detect a specific feature when it appears in the center of an image. But if that feature is like in a different position in the image another time, it won't be detected. But a kernel, on the other hand, when it's looking at like an input limit image, it's going to find every place that matches the feature it's looking for. So like this property is called translational invariance. And like for example, in this little image here with the cat, of course we know that both of these images represent a cat with a blue background, right? And if this was a cat versus some other image with a dog, we'd of course say that both of these are essentially the same, right? But we have to understand that these two images for like a normal model or something where you were putting in some sort of parameters, they would look very different because the location or where the cat is, right? Since we're using kernels though, we're able to kind of look through each of the image and still find a pattern at this part of the image and at this part of the image, and we're not looking at the whole image at once as a whole, because if we did that, this image and this image would look very different. So this is kind of a good example. So also, why exactly do we use convolutional layers again? One thing first is that convolutional layers can really handle those larger input images. And for example, like a normal neural network could be fine for something like an MNIST data set that has 28 by 28 pixel inputs, but moving to like a larger sized image or even a color sized image, which is no longer, 28 by 28 by 1, but it would be like 28 by 28 by 3, meaning there would be 3 channels for RGB layers. In that sense, we would need a lot more neurons. And some examples, if we had a 224 by 224 by 3 image, we would need almost 150,000 neurons. And even just adding one single layer would require almost 10 billion parameters. And this is kind of not really plausible in the real world. So as a result, using kernels in a CNN can be this can really dramatically reduce the number of weights needed from layer to layer. And the fact that we store the weights in kernels means that we're able to pass the same weights over the whole image. And actually with CNNs or with convolutional layers, the 152 layer deep ResNet architecture, like ResNet's like a common deep learning architecture used for image classification today. It actually runs on these large size 224 by 224 by 3 input images with fewer than 20 million parameters. So, I mean, we were showing before that if we were trying to just add, a single hidden layer, half that size earlier, it would require over 10 billion parameters, right? Here we're using 20 million, we have 152 layers. So this is definitely a lot more helpful in the real world. And just in case you guys are unfamiliar with, I guess, weights and things like that in computer vision, just storing like weights in kernels is sort of like pairing the connections between the neurons and then sharing weights between them, which is like why you see this like often described as locally connected neurons sharing weights. And the convolution operation explains why that and how like these how they locally connect neurons and share these weights. So now that we understand how I guess these convolutional layers are superior to fully connected ones for image recognition, the main problem is just figuring out how do we implement one. So if we remember from last week, a feature map is basically what you call the input, or I mean the output of like a kernel here, convolved around some sort of input image, and it's named as such because this output image would have high values or so wherever the input matches the feature that the kernel is searching for. A convolutional layer is just simply multiple kernels run over the same input. So the number of feature maps produced and then this number of features detected is determined by just the number of kernels we have around the input. So together we take these output feature maps and they can be treated as like a stack of feature maps. And like sometimes when we have these RGB images like in this little figure here at the top right, we have to stack kernels to make a filter, and this filter will help us produce this single output feature map, but we have three kernels, one for red, green, and blue, to kind of take out to find patterns in different parts of the data filtered by red, green, and blue, or so things like that. um, and essentially, like this, if we appended like a second convolutional layer, like this yellow one, the input would just be the output stack of the feature layers from the first layer, and then the output stack from the first layer is treated as almost like a multi-channel input for the second layer. And this is like essentially just how I guess these work when you have more than one kernel. And by feeding like each successive convolutional layer the inputs from the layer before, we're structuring our CNN to be able to combine all sorts of features and abstractly combine these red, blue, and green features together. And for example, like if we had like a to try to classify whether or not an image contains an X or not, like layer 1, for example, if we had a CNN, might just contain three kernels that can identify a diagonal with a positive slope, a negative slope, and an intersection. And these would kind of produce a 3D feature map stack. And then the next layer would look at them to see if the feature map from the prior layer activates in like certain right areas for an image with an X and things like that. It's kind of each of these filters is looking at a different part, kind of, if we were to explain it in just kind of a simpler way. So now we have to figure out how is our convolutional layers going to learn exactly what we have to detect, right? So to get them to learn what features to detect, and by backpropagating and updating the weights in each kernel, we need to introduce this activation function. And if you guys remember, like in our previous neural network lectures, right, a standard activation function is like the sigmoid function, or like the tan h function, or the hyperbolic tangent function. And these functions they kind of look like this, and they have a very similar shape as like the sigmoid function here is the blue one, and the tan h is the orange one here, and they have similar shapes, but I guess the tan h has a larger range from -1 to 1 compared to the sigmoid's range. But these both have the major issue, which is the vanishing gradient problem. Where like the gradients, for example, like the gradients when we're looking and trying to find these sort of minimums, right? And we're trying to figure out the good gain for our algorithm, they become really small when our inputs are extremely large or very small, since it's kind of slowly reaching that zero value. You know what I mean? So for CNNs, the standard activation function is actually neither the sigmoid or the tan h, and it's actually something called ReLU, which is rectified linear unit. And as you can see, it's a very basic function, and mathematically, all it is just taking the max of 0 and whatever value you have. So if my x is 2, it'll just the f of x would just be 2, and if it's less than 0, it would simply just be 0. So this is basically helping. So basically, the slope here for any of these the slope for any of the positive inputs or any values is just 1, and this prevents this gradient from vanishing because it's just simply like a straight line going to the origin, and this helps speed up training immensely. And the function itself and its derivative are really easy to compute, as you could tell, which really helps speed up training. And this ReLU function is applied directly to the output feature map of a convolutional layer. So, like in practice, this is really as simple as just replacing all of the negatives, like in this little matrix here, with just zeros, right? So if this was our output feature map, this would just be our, final output matrix. So, conceptually, it can just be thought of as a network only taking positive cases into account when training. And this is similar to like in real life and how biological neurons fire only when like a certain activation threshold is reached and do nothing otherwise. And that's kind of what it's trying to mimic. So besides, the activation function, another kind of important part of these convolutional layers things is pooling layers. So even with these speedy ReLU activation functions and the advantages, computational advantages we talked about before with convolutional layers over fully connected ones, CNNs are still computationally intensive. So to further reduce this cost, there's another layer you can add, which is called pooling layers. And as this name implies, these layers help pool together the different values that are spatially close together. The most common type of pooling is max pooling, where you take the highest value within a certain region, and you just kind of, based on this logic, you can reduce the size of your matrix significantly. So here, if we kind of have this 4x4 matrix here, and we're kind of splitting into these 2x2 regions, we can take this 4x4 matrix. Look at this top left corner, look at the top right corner, look at the bottom left, bottom right, and based on that, we could easily kind of figure out the max. And then basically, if we are able to take the max of each of these, sections by themselves, now our model, our final, what's it called? Our final little matrix here would be like extremely reduced in size. And as you can see, I mean, it's still getting significant information here, because this 2x2 matrix does say that there's a value of a max value, and this top left 2x2 matrix is 19, 86, 97, 60. And I guess when you look at this matrix overall, you do see some values like zeros here in the top right that aren't accounted for, right? Because we said 86, which is why another approach that another common approach is called average pooling, which is essentially the same idea, but you would take the average of each section. But if you guys can kind of see, like based on these pooling layers and ReLU, we're trying to take, I guess, the max values of like each of these categories or so, and trying to determine, trying to get the most information. But also, we're not going to, we're trying to reduce, computational time as well. And there's some drawbacks, of course, like for example, in these cases, just getting these 4 values won't really show everything that's going on here, but it's still definitely helpful. Okay, so now we can move on to talking about the fully connected tail. So we understand how convolutional layers, produce these stacks of feature maps, and then after some processing with things like ReLU and max pooling layers, they're able to be fed to the next convolutional layer, and then the next, and so forth, right? So it essentially just like looks like something like this, where you have your input, you go into this convolution, your first convolution. You take ReLU, then you have a pooling layer which takes the maxes or so of each of these categories and creates a new sort of layer, and then so forth to keep going and going and going, right? So how do we though turn the stack of feature maps at the very end into a prediction, right? All we have at the end is just the same kind of stack. So CNNs are designed to classify images well, but the current output doesn't contain the classification. So the solution is to turn back to the fully connected layer, like the dense layers we went back to in neural networks. So after we finish this, convolutional phase here or so in our pooling layers, the CNN most likely has a very high level sense of what features exist in the image, regardless of where they are in the image specifically, right? And should even have reduced the dimensions of the input image to a decent size, right? Not something like 224 by 224 by 3. It's going to be much more manageable. And in this case, this means like our main issues in the first place, like with too large of a size or things like that, have been solved. So now, well, all we have to do is just flatten this final 2D output over here, and if we just flatten this, we could turn it into a 1D array. And with this, image classification turns into like a standard just classification problem with lots of arbitrary numerical inputs and our known desired output, right? Because we know what our final output needs to be, and we can train our model normally. And at the very end, we can also just add in a fully connected layer and possibly that final function at the end, softmax, determine, which type of, in this case, I guess, which type of vehicle. Is it a car, a truck, a van, bicycle, so forth, right? You have a couple different options. And this is kind of really helpful. It kind of helps sort of seal the deal looking at the whole structure. Just if it wasn't very clear, just the flattening process is just something very simple. You have a 2D array, right? 1, 2, 3, 4, 6, 7, 8, 9. You simply flatten it to a 1D array. Just want to make that clear. Okay, so now we have softmax. So softmax is like another type of activation function, and this is used at the end of the dense layer, or like you'll see the last layer of the diagram previously was labeled softmax, and like ReLU, it's like another new activation function, and luckily it's really easy to understand. Softmax, all it does is just converts numerical outputs of our neural network into just probabilities, and with higher numbers translating into higher probabilities of being that specific output. For example, like if we had, you only use like softmax and things like that with categorical data, but if we had something like a bunch of different cities or something like that, right? We would have to do this. We would have to use something called one-hot encoding, and essentially what we would do is we would set the value of Rome as 1, 0, 0, 0, 0, 0, 0, 0, and so forth, right? If we have 10, it would be array length 10 with Rome as a 1. And if we wanted to look at Paris, Paris would be like the second value. And essentially the way what this is exactly doing is that now like the index or so, I guess, of this array that has the highest value will be like our final output. So a little better way to explain that is here. So if our model returns these, 5 values, right? Now our softmax activation function will turn these 5 values into probabilities. So now when we see these 5 probabilities, we see what's the highest probability? Okay, 0.9. 0.9 is the second value, right? And we go back to our, one-hot encoding from before, and we know, okay, if our second value is max, this is where our, our output is. Our model is saying that this second, the second value is the one that is the one that the model is predicting. So in this case, it would say that this model is outputting Paris, just because like this is the highest probability. So in the code, there's actually like easy like ways to do this with Keras. It's called one-hot encoding, and it just helps turn your categorical data into this kind of array or this kind of shape, so that it's usable with the softmax output layer and having 10 output neurons. And yeah. So now we can talk about just like the last small stuff is like hyperparameters, right? So of course with the CNNs, there's lots of different things we've talked about. We've talked about kernel size, number of kernels. There's even something called stride, which we might have discussed last week, and I'll get a little bit more into, and things like padding. And these are all kind of techniques that you can do to kind of, when you're making your CNN, things you can change or tune, and they can kind of help your model in different ways. So starting with kernel size, changing the kernel size really impacts the computational cost and forward and backward propagation and the scale of the features learned, because if you have a larger kernel size, right, you're making larger outputs or so, things like that, and smaller kernels are generally going to learn these smaller patterns, but larger kernels are essentially technically they might be more ideal in some cases, but they would be a lot more difficult to train, but they could extract more spatial information about an image. But normally, like normally use odd numbers for kernel sizes, so that the step, like at each of these kernels or each step, the center is a specific pixel and not an area between pixels. If you had a 4x4 kernel, the center would just be like the intersection. So that's why common sizes that you'll see in CNNs would be like 3x3 kernels, 5x5, possibly even 1x1s, which would just simply adjust the number of channels. And this is kind of a parameter you could mess with if you're actually coding your own CNN or just thinking about. Now we have like number of kernels. So in like CNNs, often there are many kernels per convolutional layer, and you'll see different multiples of 16 or 32 or 64. This doesn't really have any specific reason why people do it. It's just a kind of this bit terminology or so, this kind of way of making it that I guess data scientists have just adopted and kind of follow this rule for some reason. I guess they're just making these kernels these sort of multiples, and each of these different convolutional kernels, they each act as a different filter, creating like a different channel or feature map representing something different. So before I gave that example of the X, right? You'll have some kernel looking at the diagonal, one diagonal, some kernel looking at the other diagonal, some kernel looking at some sort of spacing. Example here, you could looking at edges, diagonal lines. In deeper networks, you could have like a kernel if you have some sort of like a bird or something. You could have some kernels that are focusing on the eyes, some kernels that are focusing on the wings, some on the feet. And essentially, look at all these kernels and say, does the feet match, the eyes match, do the wings match, things like that. Do they all match? Then we'll give that specific value a higher probability, right? And this is kind of an option you can mess with, right? Do I want more kernels? Yes, I'll have a higher number of channels. This would, however, create a growing amount of data, could use more memory. But again, as like happens with all these kind of machine learning problems today, there could result in some sort of overfitting or something like that, right? If you have so many kernels memorizing almost every part of the image itself or something like that. Another thing to look into is stride length. So in the examples we were talking about before, we slid these kernels, or like in the previous week as well, over every possible pixel, and our kernel just simply moved, from one set of pixels to the next pixel, right? It moved from, the top right, it moved one pixel to the right, one to the right, one to the right, so forth, right? But at each step when we're moving, like, one in the right direction, there might be some like significant overlap, as you can imagine. And if you're not, if you're trying to reduce computational time or something like that, what this would do was it would essentially like, or what the kernel size would do is if I made a stride length 2 rather than 1, then this would reduce the dimensions of our final output matrix, and the max pooling layer, like described before, we were talking about, also had like this max pooling layer back over here essentially has a stride of 2 where we're looking at this, and instead of looking at these 4 next, we kind of move 2 over. So in this case, like increasing stride length could help in that scenario. This is sort of an example of what I've been saying, where for example where in this image here, if we had a stride length of 1, we would go from here, here, we would look here, 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 so forth, right? And this is kind of that final matrix or so that we're getting out of it. And this, I guess, is giving some value information. The edges seem to be lower values than the center values here, and so forth. But if we change this stride to 2, now actually our final output is only a 2 by 2 matrix, so this kind of reduced the size a good amount. But as you can see, we're only getting 2, 4, 8, and 10, which previously were just the corners of this matrix, and we had more significant values like 24, 10, 20, and things like that from the overlap a little bit over here. So these both are kind of examples when you have different strides. So lastly, we have zero padding. So zero padding is another parameter you can choose in your CNNs. And essentially, if a kernel is centered around a bordering pixel or something, if you're looking at a kernel at the very corner of an image, it could really be missing this valuable like edge info or something like that. For example, in this case, if we just didn't add anything or didn't try to change our kernels when it was around the edge, we would get this output for this input matrix with our kernel. We'd get 21, 24, 24, 21, right? Nothing really obvious here, right? It looks very similar or something like that. But if we're using zero padding and actually add zeros all around the matrix so that the corners, I guess, or so are kind of valued more, because previously, if I'm, have a 3 by 3 and I'm going by stride length 1, this value specifically, like this 1 over here, was only used in one of my like strides, right? It's only used once, then it's never again used, because then I go into this section, then I go into this section, and then I go into this section, right? So over here, however, my 3 by 3 matrix touches this one value multiple times rather than just once, and the only values it's only going over once is these zeros at the edge, which we don't really care about. So as you can see here, we have a 4x4 matrix, which is a lot bigger than our 2x2, but we can see there's some meaningful values here towards the edge, and we can see that this is definitely adding a little bit more information that could help towards the edge, especially if our image has, something around the edge, or if we're looking at, if we're trying to classify some sort of figure that a lot of the main parts of the image revolve around what do the edges of the image look like. So just to kind of put it all together in some sort of code, if you were to kind of write some code for this or use char or something like that, and these parameters we've been talking about are very simple to implement, right? We were kind of explaining how they work, but in reality, all you would do is you'd simply start your model up. You would add your first conv layer, right? Now the first parameter you would add is the number of kernels we discussed before. So in this case, our first layer uses 32 kernels, and each kernel is 5x5 size with a stride length of just 1. You can see here we also say our activation is ReLU, we have our input, and that's pretty much all we have to do here. And it's essentially incorporating almost everything we've been talking about. You could even try something like, as one of these parameters, like padding equals and then quote same, and that would apply 0 padding as well to the kernels. Then you could add something like the max pooling layer we talked about. In this case, we're looking at the 2x2. We're going to look at the individual 2x2s matrices in a stride length of 2, like in our previous example, and then simply we're repeating that process, and eventually we get to that flattened phase, like I said, where we're taking our 2D matrix and turning it into a 1D array that goes into our dense layers. And after one of this one fully connected hidden layer with ReLU, we have our final Softmax output layer, which would give that, say we have 5 classes, it would give that array of length 5 or so, and say 0.1, 0.1, 0.1, 0.7, or 0.1, 0.1, 0.1, 0.6, and 0.1, and it would simply say, okay, 0.6 is the greatest value, it's most likely that class, right? So this is kind of just how it all ties together. And just one last thing to add, which is a little bit, I guess, beyond just talking about general CNNs, but I think it's something that's really important to learn about, is transfer learning, which is a technique where you actually have like the model like this. Now that we've talked about neural networks and CNNs, it's a technique where you have a model that's developed for one task, and you're essentially using that point where you left off with another task. Because since like these CNNs are really generic in early layers in the first few layers, and then towards the very end they become more data specific, it really helps reduce computational time and increase accuracy. Because at the very start, your model is simply just learning how to make these distinctions between just basic parts of every image. So a common approach that people use today to save computational time, improve accuracy, is like use something like a pre-trained CNN or pre-trained weights on like the ImageNet 1000 class, there's a lot of data in there. It's an image database, so that your model just gets that basic understanding of how do you even distinguish between classes, what features you need to look at in an image, and it has like this kind of basic idea. And now, of course, you'd feed it your specific data, and it would be able to learn the patterns in your data hopefully better. So this is a good technique to, I guess, look into if you're interested, and a little bit more advanced, but it's definitely something that is kind of growing today, and there's a lot of applications with transfer learning, especially in deep learning, where you have lots of layers and you're using lots of computational time, and kind of everything you could you try to save as much of this computation as you can. So yeah, that's all we have for today's lecture. And yeah, I hope you guys enjoyed or learned something. If you guys want more information, I'll be uploading the lecture, the PDF or so. It has a little bit of some things at the end, some resources if you'd like to look into, as well as, I guess, some place where you can just look at and find just all this kind of information I discussed. I think a lot of what I talked about today is covered in that lecture. And if you also want, you can still see the slideshow if there's something you missed or want to look back into. But yeah, hopefully you guys enjoyed. Well, yeah, we'll see you guys next time.